Hi, welcome back to physics. We've been working on the circuits chapter lately. Today we're going to be learning about something new called parallel circuits. Last time we learned about series circuits, where all of the current flows in one single pathway around a single loop containing everything within it. By contrast, parallel circuits have multiple branching pathways where the current can divide and go different places at the same time. Since the current travels through these different branches but ends up in the same place, each individual branch has to have the same potential difference drop. In other words, the voltage is the same across all the different branched pieces of this circuit. One question you can ask is, what's going to happen if there's a break in a branch? Say you flip a switch, or a wire is cut, or a tree falls down and snips the line. In a parallel circuit, since there's multiple ways for the current to flow, stopping the current flow through one branch does nothing to the other ones, and so you'll still have current flow passing through those other branches. In other words, the circuit will keep working. The other parts will work just fine. They won't even know. Here's an example of a circuit diagram for a parallel circuit. I know it looks pretty complicated. We've added in all the meters as well to measure all the different properties of the circuit, which does make it look a little more confusing. But it's the same general idea. On the left, we have a battery, including a voltmeter to measure the total voltage. There's a total ammeter right next to it as well. The current's going to divide at the top, going three different ways through three different Rs, three different resistors. And on each of those pathways, there's an ammeter labeled A1, A2, and A3, telling you how much current will go through them, as well as a voltmeter across each resistor, measuring V1, V2, V3, the different voltages in that branch of the circuit. So, we're starting with a total voltage of 200 volts, and we're given that the resistance of the three resistors are, in order, 100 ohms, 50 ohms, and 250 ohms. Then also we know from the last slide that Vt, or the total voltage, is equal to all of the other Vs. In other words, the potential drop across all branches of a parallel circuit, Vt equals V1, V2 equals V3, and they're all 200 volts. Knowing that, then we can start diving in a little deeper and say, okay, we have Ohm's law, and we could use it within each piece of this circuit. On each resistor, we can say V for that resistor equals I for that resistor times R for that resistor. We'll bring that up here. We've got three versions of Ohm's law. V1 equals I1 times R1, V2 equals I2 times R2, and V3 equals I3 times R3. We know all the V's are the same, so the left side of that equation will be the same each time. On the right-hand side, the I's are unknown, but we do know each R, those were given. What that means is we can solve through and tell exactly how much current will be flowing through each branch of this parallel circuit. Through the first branch, A1 will be 2 amps. In the second one, A2 will be 4 amps. And for the third one, A3 is 0.8 amps. Notice that the higher the resistance in a branch, the lower the current in that branch. The less current actually ends up within it. We also have an ammeter in place to measure AT, the total current in the circuit. Now what that's measuring is the current that you get when all three current branches join back together again. If you remember the rule about how that works, current in equals current out. So these should just add. AT will be the sum of all the branch currents, 2, 4, and 0.8, giving you a total current of 6.8 amps. We can turn that around now and say, okay, let's use our total current and total voltage in Ohm's law again, this time applied to the entire circuit altogether, which gives us 200 volts of Vt equal to 6.8 amps of It multiplied by Rt, the total resistance of this circuit. Solving that gives you a total resistance of 29.4 ohms. Well, that's funny. 29.4 ohms is less than any of the resistors that we put in there. Does that make any sense? Actually, it does. The idea of a parallel circuit is that you're giving the current multiple pathways to get around the loop, multiple ways to go. What that means is the overall resistance actually goes down the more resistors you add in, because you're opening up the circuit and making it easier and easier and easier for current to flow. So the total resistance gets less and less the more parallel resistors are added. We can also turn around and use this relation here on the left to say, okay, what is RT just based on what those individual resistors are? This equation is ugly, but bear with me. RT is 1 divided by the sum of 1 over R1 plus 1 over R2 plus 1 over R3 plus however many there are, typically 2 or 3. So for this example, RT is 1 divided by 1 100th plus 1 50th plus 1 250th, which gives you an overall RT, if you follow the math, of, hey, it says 29.4 ohms. Get out of town. So this should all match up nicely. To recap, for a parallel circuit in general, you can use Ohm's law, V equals IR, either for the entire circuit altogether or to dive down into any individual resistor, just like we did in a series circuit. And then there's a rule of thumb or an equation for each of those three things. IT is going to be the sum of the added up currents in all the branches. The total comes from all the pieces added together. VT, by contrast, is just equal to V across all the parts of a parallel circuit. So VT equals V1 plus, or equals V2 equals V3 equals however many there are. And finally, the ugly one is the total resistance, RT, is 1 divided by the sum of the inverses of the resistance of all the resistors in parallel. Hopefully that makes sense. We'll try a couple practice problems and see if we can get that to work for us. Thanks for listening today. I'll see you next time for more physics.